Hi, my name is Saima Rahman. I am in the 12th grade at Niles High School, and this is my design project on designing an isoprene breathalyzer to indicate blood glucose levels through color. To start, one of the world's largest health problems currently is diabetes. As seen here, diabetes causes deaths in the ones to tens to hundreds of millions across the globe and kills the third most amount of people in the United States. The issue with diabetes is the inability to maintain stable blood sugar levels, so low blood sugar, also known as hypoglycemia, can lead to illness in people with diabetes. Such illnesses can include diabetic ketoacidosis, which is a breakdown of tissue and absence of being able to use sugar from the blood as energy. This can cause heart problems, limb loss, nerve damage, and death if untreated, among other symptoms. A more recent pressing issue is that people with diabetes are 7 times more likely to become hospitalized and sick with COVID-19, and overall, there have been 79,535 deaths per year most recently from diabetes. So what are some solutions? So in this chart, you can see that since the 1970s, there's a general decrease in the diabetic deaths per million. And this is because of the introduction of blood sugar management tools. So here we have a Dexcom, which attaches to your arm and it regulates your insulin levels. A basic blood sugar monitor that pricks your finger and uses the blood from your finger to measure blood sugar. And the most adorable option, a service dog that can smell the chemical imbalances off of your body and alert its owner when blood sugar levels are low or high. So, as seen on the graph previously, the cases decreased but then increased after some time, and that is because of the increase in cost of blood management tools. So, here we have one of the three options mentioned previously, and this is the cheapest option. And even the cheapest option can cost up to $500 initially, plus an additional $100 per month for maintenance. The high cost in management tools makes blood glucose management very inaccessible to people in low income neighborhoods. So the goal is to design a non-invasive bioindicator that can accurately indicate low blood sugar levels through breath isoprene levels. The requirement is 1, to detect blood glucose, 2, do so through color, and 3, detect at least the main checkpoints, which are dangerously low, a safe level, and dangerously high. The constraints are that it cannot be toxic, not be larger than a handheld device, and cannot cost more than $100 for the final product. So, to understand, let's talk about diabetes in general. In a healthy person, when we eat food, the blood sugar levels in our blood increases. In response, the pancreas releases a hormone called insulin that allows the cells to absorb the glucose from our blood. This does two things. It allows the cells to use sugar from our blood as energy, and two, clears the sugar from the blood to regulate blood glucose levels. In a person with diabetes, however, the pancreas makes little to no insulin, which doesn't allow the glucose to enter the cells, or the cells become insulin resistant, which also doesn't allow glucose to enter the cells, and this causes two problems. The glucose remains in the blood, and the cells do not have an energy source because they cannot use the glucose. So issues like this can cause problems like diabetic ketoacidosis, as mentioned earlier. Additionally, when there are blood sugar imbalances, there are certain chemical changes in our body, and one of which are our breath gases. So it is known that as the blood sugar in our bodies decrease, we actually exhale more of something called chemical isoprene. Another concept needed to understand this design is a function of chemical indicators. So chemical indicators are solutions that change colors in response to change in pH. Different indicators have different detection ranges. So on this chart, you can see that this indicator detects pH from around 7 to 9. However, methyl red can detect pH differences from 5 to 7. So we have to use the proper indicator that covers the range of the pH change of our isoprene concentrations. So our subject being used is isoprene because it increases with hypoglycemia, and it's also not affected by many other stimuli, making for an accurate breathalyzer. Isoprene is also highly reactive with acids and bases, and with sulfuric acid in particular, it might make a yellow or red solid that can also be used as a color indicator. So here's our process outline. We'll have 1 beaker per isoprene solution, and in the beakers, we will have either an acid or base, or a chemical indicator. We will then add increasing levels of isoprene to each beaker, and then note the resulting color change. We will then repeat this process for as many trials as we need for each chemical indicator until we find one that is sufficient. I used 5 trials. So here, first we tested our pH. Here we have our raw data for our basic pH testing using a pH probe as seen in this picture, and here we have the summary data. We have the pH for each 5 trials for each solution, and then here we have the averages of those trials, our standard deviation, and our SEM values. Standard deviation shows how far apart the data is, and our SEM values are our error bar values, which we will address in a couple slides. Here we have our graph for pH values. You can see a general trend that as isoprene decreases, the pH increases. However, we do see some overlapping in error bars. Here's our first color indicator method, which is methyl red. We measured the wavelength of we measured the transmittance of wavelength 480, which is for yellow light, through the solution to see if there are any changes in color. Here's the raw data, and here's the averages, standard deviation, and SEM value. Here's a graph for that data, and we can also see in a trend that as the isoprene decreases, the transmittance of the wavelength increases. However, there are also some overlapping error bars. And finally, we have our last color indicator method, which is using sulfuric acid. Here you could see our solutions with our sulfuric acid and isoprene that are still clear, and that is reflected in our data because the transmittance of wavelength 700, which is for the color red. Here's our raw data for that, and then our summary data. And here's our graph representing that data, and you can see that there is no trend here, and the bars are very similar in size, and the error bars definitely overlap. So our discussion plus error analysis. For our discussion, you can see that the error bars in our pH almost all overlap except for the 0% compared to the rest, and that means that the differences in pH across the solutions are not significantly different, which means they could be due to chance and not due to the isoprene concentrations. Additionally, the standard deviation values for all of our data actually was very small, which means that all of our data was very close together. For methyl red, you have this similar trend to our pH graph, which is that the transmittance of wavelength increases as isoprene decreases. However, each of our consecutive data bars have error bars overlap, which means that the differences between those values are also insignificant. And for our sulfuric acid, the bars are almost the same size, and the error bars definitely overlap, which means that the data differences in our wavelength transmittance for our sulfuric acid and isoprene solutions are definitely insignificant. Additionally, some errors that we can consider is that the solutions may have mixed because the bottles ended up cracking in the freezer, and also there were not caps put on the cuvettes when the solutions were put in the spectroviz. So this could have allowed other wavelength lights to enter the cuvette and alter the data. So in the future, what we have to do is keep the solutions very separate, not put them in the fridge so that the containers don't freeze and end up breaking, or not in the freezer. And also, there should be lids put on the cuvettes to prevent other lights from entering. So as a conclusion, since the difference in data is insignificant, neither of those options were good indicators. Future testing is necessary using possibly a higher concentration of sulfuric acid in order to make a reaction. So we were still currently in the indicator section of our design process. Once we find that, our next steps are to find a filter to make sure that toxic chemicals like sulfuric acid are not being inhaled, and then finally make a shell that can hold everything together in a final breathalyzer device. Hopefully, the invention of this breathalyzer will decrease the overall deaths caused by diabetes, making it easy to use by it being non-invasive and using color will increase ease of use, and the low cost will increase the accessibility of the management across in people in low-income neighborhoods, which should increase accessibility overall of blood glucose management and decrease the deaths. And here are my sources. Thank you for listening.